For our customer profile, we've decided to focus on the custodial staff of PFT, and the issue that we're trying to solve is testing and determining the frequency of the stall bathroom use to determine which stalls and bathrooms need to be cleaned the most and which deserve the most attention. The other part of our project is to have an occupancy flag, which will show people from the outside, people and custodial staff, when the stall is being used. Specifically, we need our design to be tested for a week unattended. It must harvest mechanical energy, and it cannot be induced by outside forces, such as telling people to press a button to make them happy. The functions and constraints of our design were to harvest mechanical energy, convert mechanical energy, display occupancy, durable enough to last the whole week unattended, cost efficient, easy to comprehend, and most importantly, unique. The way we decided to measure this was through e-specs such as energy collected, joules, energy repurposed in joules, the counter, which is just single digits, the lifespan of our design, which is how long it could stay unattended, time of production, which would be measured in hours or days, cost of creation, which would be measured in dollars, and height raised. Our first iteration of this design was to have the gears attached directly to the sliding lock on the bathroom stalls, and the flag also directly attached to the gears, so whenever the gears moved, when the lock is moved, then the flag will turn from a sideways position to upright, indicating occupancy. And our second iteration for the flag was to have the same gear system, but instead of having the flag directly attached to the gears, it would be attached through a string system, and it would rotate in a very similar way. Our first iteration of the counter was to attach enamel copper wire to the gear with magnets onto the hub of the gear. The gear rotates and causes induction into the copper wire, allowing for the voltage to increase. This voltage will then power the Arduino, which will then make the counter go up as the gears spin. Our second iteration of the counter would be to use piezoelectric disc, which would turn physical contact into an electric pulse to change the counter. The way we would do this would be when the lock slides, it would hit the piezoelectric disc to then change the counter when the door is locked, indicating use. In the end, we finally landed on using the string method for the gears as well as the piezoelectric disc. These options work best for us because it gave us the best results for height of the flag, efficiency, and best amount of voltage to power the Arduino. Using the functions and constraints, we then put them into a functional decomposition, which we separated into sections of capturing energy, cost, and then customers and user interface. For capturing energy, we wanted the device to capture mechanical energy, recycle the energy, power our contraption, raise a flag, as well as count usage. When thinking about cost, we considered cost effectiveness, cost to fabricate, time to construct, material used, design cost, weight, ease of installation, and ease of uninstallation. When considering customers and users, we thought about lifespan, which would mean lasting more than a week, as well as durability. We also considered trying not to interfere with the user's normal routine, becoming unnoticeable, and not interfering with the stall itself.
For our design, we wanted to figure out a way to take the motion of sliding the lock of a bathroom door and using that to both raise a flag and hit a piezoelectric disc to generate a signal and count the amount of people who use the bathroom. So the first thing that we had to tackle, was how are we going to take this horizontal motion and make it raise a flag like vertically. So we did some research and we decided on taking a gear rack, attaching it to the lock, and then when we slide the lock, it'll spin one of the gears. The smaller gear will spin a bigger gear. The bigger gear will spin, and then if you think about the motion on like just the y-axis, if it's going around in a circle, it'll be going up and down. Like if you look at a point on a circle and the circle is spinning, the point will be going up and down on the y-axis, right? So we can use that ideology to pull a string down and then use that downward motion to pivot the flag up, and then theoretically the flag would be heavy enough to just fall back down whenever the lock is slid back to the left, which would like unlock the door and make it occupied or vacant. So just its own weight would make the flag fall back down. The other side of things for the counter, what we do is the lock, when we slide it, it would hit a piezoelectric disc, which would send current down some wires into the Arduino, and some complicated stuff that I'm not gonna get into. The lock is gonna hit it, and then it's gonna count one person for every time it locks, which one person, one lock, so it works out fine. So for the gears, we have one small one and one big one, just because the space works out better for the bathroom door, since space is limited around the area of the lock. We want to have like more free room to be able to slide the lock more freely. The amount that the bathroom lock slides normally turned out to not be enough, so we had to create a replacement system, and we just essentially multiplied that by 4. So we've got like 4 times as much movement, and that way we're able to get the let's say the bathroom lock it moved 1 inch initially. We're able to translate that motion into 4 inches down, like up and down. So we can pull the flag down, or we can pull the part that pivots down 4 inches, which will move the flag up, and then make it visible. For our decision matrix, we had a lot of our ideas were just a bunch of different iterations of this. So for example, instead of using fishing line, we'd have like a solid rod that would pivot the flag. But another example is other stuff we put in our decision matrix were just other design ideas, like alternate designs. For example, some of them we're gonna use the swinging of a door, right? But that would have been too like overdone. And other ones like a toilet paper dispenser. It was toilet paper dispenser. That one was just like not feasible, as well as this one that uses a trash can. So we decided to scrap those, and then we decided between some different iterations of this, very subtle differences, but we decided on just what we have now, with the piezoelectric disc and the fishing line.
Okay, I'm going to talk about the Arduino aspect of our project. So as stated previously, the locking mechanism is going to slide across when the user locks the door, and from that it's going to turn gears, raising a flag, letting other people know that the stall is occupied. Well, as on the other side of our project is that we also wanted to measure how many people use the stall in a week, so that the information could be given to the custodial services so that they can figure out how often they'll need to clean the bathroom. So what we did for the Arduino is we have the Arduino itself right here, this little black square, and then we have a thing called a breadboard right here. And so we used the pins on the Arduino and we connected them to the breadboard, and then we had a starter kit that was given to us as a part of our project that included this little digital display. It's called a 4-digit 7-segment digital display, meaning that it has 4 separate digits, each one made of 7 segments. And then if I take this out, you can see that it has a couple of pins on each side, and there are 6 pins on each side. Each pin correlates to either the digit or a certain segment on the digit. And so what you have to do is you connect the wires using these jumper wires that were also included in the set, and you connect them to a pin of your choice on the pin rack on the Arduino, and you connect them to a correlating pin on the digital display, so that when power is provided to the Arduino, and you use the system code through the Arduino IDE program, it'll provide power to the digital display, lighting up whatever you tell it to light up on the screen. So doing that will using the code that will be displayed. This code includes an online library called the SevSeg library, which stands for 7 segment, and this is a library that is a part of the Arduino code itself that is specifically made for this 7 segment digital display. And using that 7 segment digital display, a variety of functions are given with the included library. These functions make it way easier than normal because you would have to code all these functions yourself, and if you were to code power to each individual segment, it would take you a very long time and a lot of code. And so this library actually shortens the process that it took to actually code the Arduino itself, as well as save a lot of power. Because a problem with the Arduino is that we have to provide the power to it ourselves. And speaking of the power, we use a thing called a piezoelectric disc. This piezoelectric disc is made up of 2 parts. There is the brass exterior and this little metallic interior. The metallic interior provides the negative side of the circuit, while the brass side wire connects to the positive side of the circuit. Alright, so when we plug this into our circuit, we will plug the positive wire into the input for the power into the Arduino. Then you plug the negative side into the GND on the Arduino. The GND stands for the ground, which means it's the negative side where all the current will go, and then come back to loop around because it has to be a looping circuit for it to function properly. As I was stating previously, the Arduino needs to be very power efficient. And to do this, in the code shown here, we included a delay, and this delay is what tells the Arduino to keep the lights on for a certain amount of time. And what this does is it allows the digital display to be very power efficient, so it uses less voltage, so we don't have to have a very high voltage output. Obviously, one of our constraints is that we still wanted to have a high voltage output because the more energy generated is better. So that finishes the Arduino portion of the project.